Hello everyone, and welcome to Class 3 on correlation. I'm so delighted to have you here today, and we're going to jump right into the lesson. As usual, we're starting with course objectives, and you're always welcome to stop the video and consult the PowerPoint to see what today's objectives are, as well as the overview of the lesson. There are a series of correlation coefficients that we're going to discuss. We will discuss some of these in more detail than others, but this is the short, long, however you want to put it, list of correlations that are pertinent to this lesson. To just set the stage for us on, I guess, this correlation question, let's look at a few variables that really kind of drive how you decide which correlation coefficient to use. So there are three types of variables that are going to be pertinent to today's lesson. We're going to think in terms of true dichotomous and continuous dichotomous variables. So a dichotomy, yes, no, is one example, and we'll look at another example of a dichotomy in a little while. And right here you can see the example from the survey of are you a member of 4-H, yes, no. Then the ordinal variable, in this case we're showing age as an ordinal variable, and this will be important for you to remember because I almost always talk about age as a continuous variable. It's been years since I collected data this way, age as an ordinal variable. But occasionally I'll work with other researchers who've already collected their data, and they will usually collect it in an ordinal manner, and it may look something like this. So today we're going to use age as our ordinal variable. And then we'll do continuous, and for our example today, we're going to look at continuous as a construct, so creating either a summated score or a mean score. Usually when I'm doing my work, I'll create a mean score as opposed to a summated score. Regardless, you're taking the items, however many items you have in a construct, and you are either averaging them to get your mean or just adding them up to get your summated score. So that's just kind of the brief overview of the three types of variables we're going to use in looking at correlations today. All right, so correlation is all about the relationship of one variable to another, right? And as you look at this scatter plot, you're probably going, I don't see very much going on there. And I agree, I don't either. It looks like those dots are just all over the place, which suggests to you that there is very little to no relationship between whichever two variables were used for this particular one. On the other hand, when you look at this particular scatter plot, you see that those points are beginning to really cluster around that center line. So you see the line and you see the cluster. That's what you're looking for. The tighter the two variables cluster to that line, the stronger the relationship. So you've got a fairly strong, maybe it's more of a moderate, how you term it's debatable looking at your scatter plot, but regardless, what you can see here is that you have a positive relationship. So look at the direction that the dots are going on that scatter plot, and that tells you that you are moving in a positive direction. Okay, and then we will compare that to dots going the other direction, and at this point you can say, that relationship must be negative. Again, it is a very close grouping of the dots to that line, suggesting a stronger relationship, but going in that other direction lets you know that it's negative. And I will go ahead and tell you right now, and this is the last point at which I use any visual interpretation of a relationship between two variables. From this point on, everything I do as it relates to correlation uses the numbers. So I don't usually put together a scatter plot. I'm not going to use that as my visual. I'm going to use the hard numbers because that's that's just how I always report my data. So we're going to move on from the pictures and on to the numbers. All right, so I have mentioned to you in previous lessons that we're going to talk a bit about power calculations. We're not actually going to calculate the power for correlation in this lesson. Instead, we're going to look at the information that is provided on this slide and the next slide, and we're going to talk about what kind of information might be put into a power calculator. We're going to talk about what kind of information might come back out of it, and then we're going to talk about, how that is helpful to us in terms of either collecting our data or justifying some of the relationships that we have at the end. All right, so we will come back to this effect size chart that's here on the bottom of this screen a little later on in the lesson, but this is something that you could write down or take a snapshot of, or just maybe even print out that slide from the PowerPoint that you've got, because we will use this effect size piece throughout the semester. In fact, don't worry about snapshots or prints or anything, because I do have a handout on effect size. I'll get that uploaded to the Moodle site for us. All right, power calculations. Now that we can ignore effect size, right? We will discuss this again one more time in this lesson, but it's later on. Let's talk about a priori computation of power. So power is what helps us, well, the cut and dried of it is, when you know what the some of the relationships are between your variables, and you want to get to power of 0.8. Remember, we discussed that in the lesson about power. You know the relationship, you know your alpha, and you know what power. You've got enough information to be able to say, okay, now how many surveys do I need to collect to be able to get to a power of 0.8? And so in this particular example, you knew ahead of time that the relationship between two variables was 0.41. The only way you could know that is if other studies had been done on these particular two variables. So if no studies exist, you could not do this computation before you did your study. But a priori computation of sample size is definitely helpful when prior research knowledge exists. All right, so again, in this one we knew that the relationship between the two variables was 0.41. We've talked about before, most often in social science, alpha is set at 0.05, right? So you see that in the second box, alpha 0.05. We know we want a power of 0.8. Remember the 580 convention that we talked about? All right, 0.05 for the alpha, 0.8 for power. We're going to set the correlation hypothesis at 0. So you plug those numbers in, you tell it to calculate, and notice right here where it says type of power analysis, it says a priori. Okay? You've got to make sure you hit the right one here. This is G-power, by the way. When you hit calculate, you come out and you see over here that your actual power is 0.8. Okay, you set alpha at 0.05 and you have achieved your alpha, your power of 0.8. How many responses do you need to your survey? Total sample size equals 44. That's pretty doable, right? So you know if you've got 45 complete responses, you're going to have a power of 0.8 for any other analysis in terms of the relationship between those two variables. Now that's all it's good for, is the relationship between those two variables. But at least you know if you're going to do another study that's looking at that relationship, If you've got that kind of response rate, you'll be good in terms of power. But really more often, we don't know. We don't know how many surveys to collect ahead of time, because we do not know what the relationship of the variables is until the study's conducted. And this is because we're not usually doing replication studies, right? We're usually doing something brand new, potentially a new survey, just never asked these questions before kind of thing. And so when that happens, that's when you cannot do any kind of a priori power calculation. Instead, what you have to do is compute it post hoc. So you find out what your power is after the fact. Not usually something to be afraid of, because most of us will overdo our sample in, I guess, in a measure, as a strategy to increase power. Because we don't know what it should be, we over collect. All right, so now let's use this example. You didn't know ahead of time. You had to collect extra surveys. You collect your extra surveys. In fact, what you did was you went out and collected 218 responses to your survey. Again, we're going to use the example of two variables that have a relationship of 0.41. And you had already set your alpha at 0.05. All right, so pretty much the same question we had on the previous slide, except now we're saying we didn't know what the relationship was beforehand. We found that out after the fact. After the fact, we found out it was 0.41. Our alpha had been set at 0.05. We collected 218. Well, what's our power now? Well, if you look over here on the power line, it says 0.99. So that over collection was a little bit of overkill, but there was no way to know ahead of time, right? Did the best you could, did your power calculation after the fact, and it paid off. Okay, so once the question of power is decided, whether it's something you can figure out before your study starts because prior research knowledge exists, or it's something you know you're going to have to do after the fact because you don't have anything to draw on, then you have to move on to, okay, I'm going to do correlation analysis. What are some assumptions? Well, the only one we really need to be concerned about is Pearson. So we need to look at the assumptions for Pearson's R. Pearson's consists of two continuous variables that we're going to look at the relationship between. And so when you've got two continuous variables that are going to be part of your analysis with that parametric data, we do have to meet some assumptions. In this particular case, we've got two assumptions we're going to look at. One, interval level data for both variables, right? And two, that the data is normally distributed. So you want a normal curve, not one that's got skew, either positive or negative in it. The other kinds of correlations that we're going to do is what we call non-parametric analyses. They're using either the dichotomous or the ordinal variables, and they're not going to meet any assumptions. And that's the point of the non-parametric. You use non-parametric analysis when your data does not meet the assumptions for the parametric analysis.